everyone, my name is Alex Kingsbury from Enlight, and I'm really pleased to bring this next talk to you today. It's by AMCM and Fraunhofer IAPT. AMCM has done an amazing job in really bringing beam shaping to the market, really pushing it into the hands of users. And they've been very well supported too by Fraunhofer IAPT and all of the excellent research that happens there and being able to really underpin a lot of that machine development with some fantastic research. So today we're going to hear from Felix Bauer, who is the head of sales, and also Dr. Philipp Kohlwes, who is the head of L-PBF, laser powder bed fusion for Fraunhofer IAPT. And they're going to talk about the power of beam shaping. So take it away. Thanks, guys.
You, Alex. So I'm a little bit exhausted because I just arrived, to be fair. So a little bit breathing will be there. So Felix, before we go into the details of, more into the deep topic of our talk today, let's stick to the market first. So I'm interested in the market feedback for your L-PBF systems, which are equipped with an AFX system. Did you receive a lot of positive feedback from the market, or have there also been some negative voices?
Hey. So, first of all, well, sorry for the inconvenience with Deutsche Bahn, but we all need to live through that. Coming to the market, I think what we saw in the first place was some hesitance, for sure. People wanted to get their hands around the topic, didn't really understand. But I think in the first place, when you learn, you start from what you know, from a standard Gaussian beam. You can only grow from there. There's not so much hesitance. And also, I think in the first steps, we really worked together with some institutions and universities such as Fraunhofer that helped to bridge that gap quite a little bit.
Okay, and you mentioned research institutes already, and are there specific sectors which are interested in these systems, in these system technologies, like your systems equipped with an AFX, or is it broadly spread across all AM users?
Well, I think in the first place, it is the typical users we see today. So there's a heavy overlap for the aerospace and defense industry that use that technology at all. But I also want to say there's also quite a big interest for general folks that just are interested in technology itself, want to learn what can be done. And then, of course, heavily from the research institute side of things that want to get around it and understand it and help then further to implement it.
Yeah, I can totally underline what you just said with regard to the aviation industry. It's also one of our pushing markets. What is my feeling at the moment for this technology? So, like first mover. And as a part of your strategic planning you did in the past, you will certainly have thought about possible annual sales figures for your Flex system. I hope so. And do you currently assume that these systems will be a future cash cow for you, or is it like one of many options you will have as a modification or customization for these systems?
Well, I mean, in the first place, for our machines, the laser is the main tool. So we look at the Enlight or the AFX laser mainly as one more tool in the toolbox, to be honest. But I gotta say, it's a pretty decent tool, and we use it a lot. And especially when moving to larger systems, more bulky parts with filigree sections, all that, then it starts to shine. So we can see definitely a pickup in the technology. We see a pickup of interest, and I think it will take a larger stake in the technology moving forward.
Mm-hmm.
But I think also what you talked now a lot about moving forward and all how these things come in place. I think it would be really interesting also to learn a little bit about the technology from your perspective and how Fraunhofer IAPT is working. How can you get your hands around that? How is that all working out for you?
You mean in general how Fraunhofer work, or with regard to the beam shaping topic?
With regards to beam shaping, of course, sorry.
Okay, so our first steps in the past were that we thought about, let's take a look at the laser market in general, because there are different laser applications, as we all know, like marking, welding, cutting, and so on. And therefore, from my perspective, each market has a specific requirement, and this requirement needs to lead to an adaptation of the specific beam shape. Because if you cannot compare a welding process to a cutting process, for example, and therefore, if we're looking, for example, at the biggest market, which is like more than 40% is cutting market for lasers, they all have Gaussian beam profile, and the Gaussian beam profile leads to an excessive overheating in the middle of this or in the center of the beam. And this is good for the cutting process, of course, but is it the best solution for a welding process? In my opinion, not. And although these lasers work for the L-PBF process. So when the L-PBF process was developed, it was like, okay, let's use a laser which is existing with a Gaussian beam profile and then test it in an L-PBF machine. And they work very, very good, as we all know. So otherwise we wouldn't be here. And is it the best solution? In my opinion, not. Because if you use a cutting laser for a process where you want to add material, it's not optimal. And therefore, other beam profiles like ring profiles definitely make sense. It's comparable if you want to eat a soup with a fork, it works, but it's not optimum to do so. So I prefer using a spoon for this. And therefore, I use like also ring mode profiles to do an additive production process.
Well, talking about the right spoon, do you see any advancement in that regard? Like, what do you see the future has to bring here? What are your thoughts about how that beam shaping should develop?
So at the moment, I see only advantages by using this technology. We did a lot of research in the past years, like 10 years or more, and we only saw advantages so far. And you, of course, have slightly additional higher costs, but they are quite quickly amortized. And this is mainly the only downside. And therefore, I see that there's more relevance for beam shaping technology in the near future. And it can, in my opinion, be the new standard in a few years also, because we implement it, you implement it as a machine supplier, and all the market will get up to this topic and is already or has woken up. And we got a lot of contact. You have a lot of contact. We will later go to the use cases. And there we see some potentials, how we can use it, and that it might be a new standard in the future.
So for you moving forward, definitely this for beam shaping. Or is there anything else you would like to say that has to be developed any further, or are we there yet already?
So in my opinion, let's tackle this question from the side of how beam shaping developed. To get an impression what is necessary for the future a little bit, if this tackles your question. Because
that's pretty much it, because we see so many options how to shape a beam, how to go there. There's plenty of options out there. Why do we talk about that one so specifically?
Yeah, so in general, there are different possibilities of shaping the beam. There is dynamic beam shaping and static beam shaping. This is the main differentiator, and then there are subcategories like static beam shaping with apertures or field mapping or via homogenizing, or dynamic beam shaping via SLM, so spatial light modulators, acoustic opto deflectors, deformable mirrors, and of course the new generation of fiber lasers. And therefore, there are different possibilities of shaping the beam. We have tested a lot of them, and they all have advantages and disadvantages. The main differentiator there is the costs versus the process stability, so to say, because sometimes for the cheaper system, you need to recalibrate everything a lot, like sometimes every build job. To recalibrate the whole optical bench. Yeah. Sometimes it's more cost intense, but you do not have these calibration problems, and everything works fine out. So you always have advantages and disadvantages. And coming to the future, from which was the second part of your question, is that in my opinion there will be more complex beam shapes in the future, even more than these ring profiles. Definitely more complex, because if you simulate these processes, the ring is very, very good, but not the optimum, of course, because if you can see the Gaussian beam profile, the step from Gaussian to the ring is like factor 2 or 3 or whatever times better. If you want to have a smaller percentage on top of this, so not 2 times or 3 times, but small percentage more, you go with other slightly different beam shapes, which are not constant but also dynamical in the future. So I think there will be more complex beam shapes in the future, but also for a reasonable cost. So the cost will also decrease for these technologies. So as we just discussed a little bit about also the point of integrating these systems. I mentioned different possibilities of integrating them, and sometimes these integration of beam shaping technologies can be quite difficult and make some complex adjustment for the L-PBF process necessary. What were the biggest challenges AMCM had while integrating the AFX into your product portfolio, so in your FLX series?
So from our point of view, it always is like three main pillars. It goes from optics, so the optical string, not just the laser. It also includes all what's in between there and the scanners and the lenses. That's the first part we have to take under control. That's like the basis of everything. And then this is I want to say, a very quick race together with airflow. So those two. And then the third pillar is always the thermal management. When we're talking about our Enlight AFX laser adaptions, it was always those three. And it comes to an extreme when we talk about the very large systems where these things all get multiplied by each other. So in the first place, we have to make sure the laser is right, it's stable enough. We have the rest of the optics in check. And we make sure we have a proper airflow, and finally the thermals. If one of those doesn't work, the whole machine will just do not the trick that's what's supposed to do. But that is like the base. Those three pillars: optic, airflow, thermal management. Those three you have in check, you're done. And that's the same thing with for the AFX. Same thing.
Okay, very good. And can you already indicate what other AMCM systems in the future might, or can we expect in the future, which are equipped with an AFX laser, or is it too soon to answer this question?
No, we're pretty much there.
Okay.
I want to say there's pretty much the whole portfolio we're doing right now, starting with the M2s, our smallest version, up to the very big one we just released, the 8K, will have AFX laser options in it. So it's the whole bandwidth, and no matter what application will work for you.
Very impressive. And as we have talked about in the beginning, more from the market side, then we went over to the machine adaptations which are necessary, and I gave some background information about beam shaping technology. Yeah. Let's combine all these topics together now and talk about use cases. Of course, we both have the problem that our customers and partners do not want us to talk about their applications. It's a pity, I know. Yeah. But maybe you can give some insights about some of these projects or use cases where you are, or which you can share.
I mean, talking about real world cases, the majority of them is, well, we have some ITAR restrictions, stuff like that. But I can definitely say we started out with Inconel applications, more on the hot side of things, majority in engine-driven application. And then moving forward, we see more and more general industry stuff. So we have a couple of customers that work with tool steels, for example, where you have, again, bulky and filigree sections. And then, of course, in the recent months, especially working together with your team, we saw also the first applications going in different alloys, such as titanium. And that brings us to the application we brought here today. Oh, we hope so. That is one of those where the technology can really shine. So we have the one that you see over here. It's an hydraulic manifold, which always by nature has filigree, pretty bulky section, where we really can bring the technology in and have a great adoption of the thing, to say so. So, and I think that comes naturally with another question: how do we get approached by that? How do we come along with that? What's the role? How does a customer approach us and get such a case study going? How can we get to such an application from your side?
So if you have such an application and contact us as one solution, or
exactly, because this was my whole take in the beginning, but I explained a bit that we were having the technology adapted in the first place in institutes and people trying to get their hands around. So how does that getting hands around with you look like?
Okay, so in most of the cases, when a customer came to us and has no idea of how beam shaping works or L-PBF in general or whatever, it's that we make a feasibility study for their specific product. We look at the material, we look at the part and try to see the optimum, and then often, like in the majority of the cases, it's relevant with regard to productivity. So all the customers are talking about productivity. Sometimes, but it's less, unfortunately, but I'm a big fan, is process stability. So second degree is then process stability. They ask us, okay, how we can improve process stability, but we are not so interested in productivity. That's less the case, of course. Makes sense because economics. And there we do a lot of investigations. So with regard to productivity, we had with different materials. We have tested titanium, aluminum, different alloys, copper, what else? Steel, different alloys, and so on. So a lot of different materials with different beam shaping technologies. And there we also try to see which technology is the best for our customer for this specific application and also for their business cases in the future. Because one application is not enough to get an idea of what the customer really needs. I think it's the same for you when you customize a machine, that you always ask, but what after 1 year? What do you do then with the machine? Because it's not depreciated after 1 year. Otherwise, it would be very, very high of costs. But yeah. And the third point, so productivity increase, one of our major points, process stability, second point, and then we do a lot of consulting also, where we see necessity, especially with regard to the beam shaping technology, that you have a very, very high degree of freedom and that some people are overwhelmed. It makes sense because they do not want extra degrees of freedom. They simply want this part printed. So they doesn't care if it's index 6 or index 3 used or whatever. They simply want a good part at a very, very high productivity, so which equals low cost, at a very, very stable process, so high process quality. And this is what the customer really wants from us, and therefore we also do a lot of consulting there. And to underline what you said, and I intermediately also underlined, the biggest markets at the moment from my point of view is mobility in general, and then these two sub areas of aviation, and then automotive. Both are very, very frequently in our house or in our projects involved at the moment.
Yeah, I think that's good to hear, because I think this bridging the gap and coming from a great idea, great technology, but how can we adapt it in a real world case? This is where usually things become critical and don't get stuck somewhere. Talking about these many applications, those customers you see, with that being said, what would you see the future of beam shaping going? Is there that same area, productivity, or are there other fields where you see that could be interesting?
So productivity is always the main driver because of costs, but there are also different possibilities. So productivity is one. The second one is process stability, which I already mentioned. Third one is that you can directly influence the microstructure in these areas where you want to have it, because the different melt pools and the different melt pool behaviors leads to different effects with regard to the microstructure. So you have different cooling effects and therefore also resulting different microstructure. This is a very, very good possibility of influencing it. You can also have different overhangs by using beam shapes, because the energy input is not that deep. You're not having like a keyhole welding process anymore. It's more flat, the melt pools, and therefore you can also get rid of some surfaces based on the staircase effect and so on. Yep. And therefore I also see the increase of the process regime, because sometimes the process is not running, even if the machine says it's 100% all the same values. There are slightly different differences within a machine, of course. And therefore, sometimes using a Gaussian beam profile leads to the effect that you are running out of these boundaries, and therefore sometimes you get some pores where you normally do not have pores. And the process regime by using these ring shape profiles is much wider, and therefore you're not running so fast out of these boundaries, and therefore this is also a very, very nice indicator for process stability, which goes along. Yeah.
Thanks. I think that's a very interesting perspective. Not just the pure productivity with the bigger beam, which is obvious, also getting more into more stable processes, having different grain structures, less overhang. That's amazing. That's good stuff.
Maybe to put it in some numbers, because everyone here is maybe interested in numbers, I guess. So with regard to productivity, we were able in the past, different alloys, you cannot generalize it, but in the past, a fair comparison, it's always necessary to make a fair comparison and not comparing, for example, index 0 and index 6 directly with each other, because they have different beam sizes and so on. But for fair comparisons, we were able to increase the productivity for some alloys 2 to 3 times approximately, and this leads to a cost decrease of 15 to our biggest value so far. Our biggest case study was 46% in the total cost of ownership of the part at the end. The 46 is pretty high, because in this case there were no real post-processing of the part. So, and therefore the quality assurance and everything and the post-processing which was necessary was not necessary, and therefore the cost decrease was very, very big. But I personally assume a good value is like 15%, 20% of the total cost of ownership if you can increase the productivity of 2 to 3 times. This is a rough value. With regard to, or to put in perspective, the process stability, we have made some measurements, because you cannot directly measure the process stability, but the best indicator for process stability is the spattering of the melt pool. Because if you have inhomogeneities or an inhomogeneous melt pool, then the melt pool is unstable, and this then leads to the fact that you have spattering appearing. And we have made a lot of analysis with regard to spattering, and there we can also reduce, in a fair comparison, the resulting spatter from 2 to 6 times. So 2 to 6 times process efficiency was increased, which is a very, very high number. And you can visually see it sometimes, that if you you see one process with a Gaussian beam shape, and you see a ring mode process, you see direct changes.
Sure, I think that's overall it's a great perspective, and I think that underlines again why we're interested, especially in the early phase of technology, why we were so keen on working together with you folks, just to get things moving and help our customers finally to reach those results. Well, I think with that being said, we're pretty much at the point. Are there any questions here from the audience?
So my question is, for AM, ring laser or planar, just like head, which is better?
What was the question? Green laser or?
Ring laser and the planar, just like head.
You mean top hat? The top hat profile?
Yes.
Or ring? Or what do you mean?
Which is better?
Okay. Better is always relative. But to generalize it a little bit is, I think Enlight has a very, very nice diagram on their website. I don't know if it's somewhere here, but you can see if you have a ring profile, or let's start with a Gaussian profile. You have a Gaussian profile and you see the laser intensity over the X coordinate. Then you see it's still a Gaussian energy input or temperature profile. If you use a flat top beam, then you have still an... Sorry?
So I just want to know Gauss, ring, and height.
Yeah.
Which is better?
Yeah, with regard to the temperature, the resulting temperature profile, this is then if you use the ring profile, because of the heat transfer in the ring, then this will lead to the effect of the flat top as a temperature profile, which is very, very nice. So the ring is preferable for most cases, not for all, but for most cases is a ring preferable compared to the flat top profile. But there is, as I mentioned, a very nice graphics on the website of Enlight, which underlines this. And
Yeah, and I'm happy to share that with you after the presentation here. Sure. So, Philip, Felix, one of the questions I have is, of the material systems that you have studied, what rises to the top of being perhaps most challenging, even with beam shaping, and which material systems benefit most from going to a ring distribution rather than a Gaussian?
You want to start?
Okay, most challenging. So in our study so far, the ring profile was always better than the Gaussian profile. So compared the Gaussian profile with the ring, it was, so to say, easier within these ring profiles. Really hard were none, in my opinion. And what's most challenging, I would sometimes say a specific steel alloy. Alex might be say copper, but there is no general answer. So there were no real big challenges. At the moment, I have one specific question mark to the spattering effect of one specific alloy. Cannot mention right now. This is the only question mark I have so far, and we will definitely do some research on this.
I would stick a little bit to what Alex would say. I'd say copper's a little bit an issue, but maybe with 2 kilowatt, you up the game there, and it has to be looked at differently. But for me now, it's the copper and partly aluminums. But I think the 2 kilowatt might fix that.
Yeah, to underline this, we have presented at ICALEO last week, 2 weeks ago, about copper processing with the AFX laser. It was a 1.5 kilowatt laser we have implemented at the IAPT, and we did some studies. And there we found out, or especially Alex found out, that even we used up to 1,350 or something watts at the base plate. And there we found out that it works very, very good, but it's still not sufficient. So we can put more and more energy because of the high reflection of the material, and therefore the two we are welcome if we can test the 2 kilowatts system in our facility. But yeah, this is sometimes this can be a little bit tricky, and therefore I also would underline copper is maybe the most or the alloy which benefits the most.
Got it. Thank you. It's kind of the feedback that we've been getting. People that have been using beam shaping have really been asking for more power for aluminum and copper alloys. So that kind of squares with your experience. Yeah. Well, Felix and Philip, thank you so much for sharing your perspective. We really appreciate it. Thank you so much.
Thanks for having us.